Okay, so to get started, I've opened Visual Studio 2013 and I've created a new blank solution called Test Demo. Now the first thing I want is a project to hold my unit tests, so let's add that now. I'll create a new project. It'll be of type class library and let's give it a name of testdemo.unittests. Click OK and let Visual Studio add that. Now, before I go any further, I'm going to need a couple of NuGet packages, so let's add those now. If I go to my Tools menu, from my NuGet Packet Manager, I bring up my console window, and the first thing I want to add is NUnit. So I'm going to install version 264 specifically here because that's going to be compatible with my version of ReSharper. And the second thing I'm going to need is a package called MOQ. And we use MOQ later on to demonstrate mocking of interfaces in our unit testing. Okay, so that's my setup complete. Now we have our project set up, so let's think about starting to write some tests. And the first thing I'm going to do is use this class 1 and rename it. And let me just refactor accordingly and change the file name to match. Okay, so I have this strongly named class now. That describes exactly what it's doing. So let's create our first test. Now I'm using ReSharper templates here to inject test method name templates. And the format I use is usually the unit under test, which might be something like a method name, the scenario under which I'm testing, and my expected outcome. So let's give this test proper descriptive name. And the first test I'm going to be conducting is calling my add method. I'm going to pass it an empty string and I expect that it should return me 0. So my test is going to look something like this. So we have this notion of a string calculator. Now this string calculator doesn't exist yet, so that's why it's highlighted in red. And my expected result from the test is going to be 0. And the actual result I get is going to be populated from calling the calc.add method and passing in just an empty string. And then I'm going to assert that my expected result and my actual result are equal. Now, as you can see, we don't have a string calculator yet, so if I just use ReSharper to create that for me, and I'm going to create it here in the same file. For now, I can always move it later into its own namespace, but for now I'll use it in the same file because it's easy to edit here. And I also am going to need this add method. Now with test driven, so that right now that allows me to run, that test is now runnable. So to run any unit test, I can click Control U followed by L. And you can see here in my output window, we get our NUnit test manager, and it's telling me that that test is failing. And of course it's failing because I'm throwing this not implemented exception. So with test driven development, we usually work in increments, and we usually do the simplest thing we can to get a particular test to build. So the simplest thing I could possibly do here would be to just return a 0. And if I now run my test again, I now have a passing test. Great. Okay, so let's move on to test 2. And for test 2, I'd like to test adding of just single numbers. So if I pass in a 2 or pass in a 5, I should get back the corresponding 2 or the 5 as an integer. So let's add this new test. So you can see here the unit I'm testing is add. The scenario is single numbers, and the expected result is returns that number. So again, if I create a new instance of string calculator, this time I'm just going to pass in a 3. My expected result is 3. I'm passing in the string 3, and I'm doing my assertion here. So let's run our test and see what we get. And you can see, okay, so test 2 is failing. So if we come down to our string calculator, what's the simplest thing I can do to get test 2 to work? Well, I guess it's going to be something like int.parse. While we're here, let me refactor this parameter name. And so we're going to parse that parameter. So let me try and run my tests again. And we can see now test 2 is working, but I've broken test 1. So let's remind ourselves that test 1 was passing in an empty string. So I guess the simplest thing I can do now to get test 1 to pass would be to check for empty strings coming in. So I can say something like if string is null or empty input, then just return 0. And now if I run my tests, I've got 2 tests passing. Fantastic. NUnit allows us to use parameters in our tests. So let's take the last test we've written and refactor it to use parameters. So the first parameter I need is my input as a string. And my second parameter is going to be my expected result as an integer. So int result, like that. I can then refactor my test, so I can get rid of this local variable. I'm going to be adding what I pass in, which is the input, and my assertion then can stay as it is. So my assertion is checking that my expected result and the result are equal. And so up here then I can change this attribute to be a test case. And you can see test case then allows me to pass in parameters. So my first test will be if I pass in the string 1, I should get back an integer 1. And so let's now run that to see does it still work. And great, that works. So if I were to pass in a number of those parameters like that, so you can see here we can now bulk up our actual test count very simply using these test case attributes. And you can see here down here now I've got 6 tests written. And by the way, NUnit, the way NUnit runs these is that it takes each one of these attributes and runs it as an actual test. So if one of these were to fail, it would highlight which one is failing for you. So for my next test, for my next trick, I'm going to see if I can get the calculator to add multiple numbers that might be contained in a string. So let me create my test signature. And again, the unit I'm testing is the add method. And this time my scenario is multiple numbers. And my expected outcome will be sum of all numbers. And so my test might look something like this. You can see here, so again, we're just creating a string calculator. And this time we're passing in a string that looks like 1, 2, 5. And so my expected result of adding those numbers would be 8. And then I'm doing my assertion. So let's run this test and see what happens. And you can see here I'm getting a test fail. So if we come down to our string calculator and have a look at our add method, well, obviously the problem is going to be here. We can't parse a string that looks like n, n. So how might I refactor my add method to get this new test to work? Well, maybe if I do something like this. So again, I'm keeping my check for an empty string in place here. But now I'm taking my input and I'm splitting it based on the comma into an array of strings, creating a local variable for adding. And then for each number in my array of number strings, I'm taking an int.parse of that and adding it to my total. And then I'm just returning my total. So let's run my tests now. Control U and L. Let's see what happens. And great, we see that makes it pass. And also we can see all tests are passing, so I haven't broken anything previously, which is great. Now again, I can refactor this method to use parameterized inputs. So let's do that now. And that might look something like this. So here's all my test cases. For 2 and 3 should give me 5. 101 and 20 should give me 121. 3, 8 and 10 should give me 21. And you get the picture. So again, let's run these and see, make sure everything is working. And you can see now we have 10 passing tests. So we're flying it. Now at this stage, you might notice that I'm doing a lot of this sort of stuff. So string calc equals to new string calculator. You can see it again here, string calc equals new calculator. And I'm kind of breaking the dry, don't repeat yourself rule. And in testing, we want to be somewhat dry and somewhat damp, and damp meaning descriptive and meaningful phrases. So in order to future-proof my test harness against possible refactorings of this string calculator, and in particular its constructor, I might want to create a method up here at the top of my test harness, a small factory method to give me a string calculator. It might look something like this. So it's just a method to get calculator, and in this method I'm just creating a calculator and returning it. And so down here I can refactor string calculator, calc is equal to get calculator, and I might do that throughout my code. So anywhere I have this line, I can replace it with this line. And I'm now using this factory method everywhere to get my string calculator, and we might see later on how that's going to jump in and save us a lot of work. Well, so far our tests have assumed happy path outcomes, so let's now think about unhappy path and the scenario whereby we get passed in an invalid string, for example. So let's create a test that might look something like this. And for now, let me just get rid of this attribute. I'll come back to that in a minute. So here we're passing in a string of a, 1, which obviously we can't add. We're calling our calculator, and we're calling add on that. And let's see what happens when we run our test now. Well, we can see here we're getting one failing test, system format exception. But that's all very well, but it's kind of out of our control. We want to be able to assert that we should be getting an argument exception in this case, and we should be able to check for that exception coming back. So how might we refactor our test? Well, first of all, we can use this attribute called expected exception. This will take a type of parameter, and we want this scenario to throw an argument exception. Okay, so that's our test decorated. Now let's run our test again, and again we should see a failure, and we do. So if we come down to our code, here's our add method, and we now have this scenario whereby we can't just assume that this array of numbers are always going to parse into integers. So how might we refactor our string calculator to handle this? Well, maybe if we add some kind of method here called try to parse to integer, which takes an input. If the try parse fails, we throw our argument exception, otherwise we just return the parsed number. And up here to our add method, we can then call on that. So we can say try parse to integer our number. And now coming back to our test, let's run this test and now see what happens. And you can see here, great, we now have 11 tests passing. So for this test here, we're actually expecting to get an exception thrown of type argument exception, and that is indeed what happens. Great. Okay, so again, we can refactor this test to use parameterized inputs. Might look something like this. So you can see here I'm throwing in all sorts of rubbish at it now. Throwing in commas and alpha characters and slashes and dashes and all sorts of things. And hopefully, if I run this now, all of these should throw the exception, argument exception, and indeed they do. And I now have 15 tests passing, which is great. So on from our considerations with the unhappy path, we might start to think about edge cases. And so for me, the first thing that springs to mind is minus numbers. Can I handle those? So if I write tests that look something like this, where I'm passing in a string that looks like -1, I should get back -1. If I pass in a string that contains -1, -5, and -12, I hopefully will get back -18. So let's try those. Run those, Control U, and then L. You can see all my tests are passing, so that's great. What about a case where we pass in a minus number and a plus number? So let's try -1, 5, and that should give me, I believe, 4. Let's try that. And so I now have 18 passing tests. So that assures me that our current code base is well able to handle these types of scenarios. Moving on, the customer has been in contact and they have a new requirement, and that is whenever the result of an addition happens to be a prime number, they want that number saved. As of yet, they're not sure how they want it saved, but that's okay. We can move on and work around that for now. So where we have this new requirement, we're going to think along the lines of some new logic inside our string calculator that checks for a prime number. And if that happens to return a true, we're going to call some type of save method. And so that leads me down the road of thinking about interfaces and mocking. Thinking about how we might approach testing this new requirement. Remember, we're using test-driven development here, so let's start with the test. and our signature might look something like that. So our unit under test again is the add method, where the result is a prime number. We should be getting back the fact that the results are saved. So let's start thinking about this test. Well, we don't know how save is going to work yet, so that leads me to think about interfaces and stubbing or mocking. And you saw me earlier on adding the moq NuGet package, so maybe now is a great time to introduce that. So let's start with our test. Our test might look something like this. If we refer to our moq library, you can see here we get a static generic method here that takes moq of some type, and in this case I'm going to create some interface. I don't know, maybe I might call it iStore. And this is going to define how a store is written for saving. Moq iStore, moq store, is equal to new moq store. Now this interface doesn't exist yet, so that's why it's being highlighted in red. And then we're going to need some instance of a string calculator. So string calculator calc is equal to new string calculator, and this time we want the string calculator to accept this iStore type. So we're going to pass in our moq store dot object, and the dot object property is how we would refer to a moq of some interface. And then we can say var result is equal to calc dot add. Let's see what will give us a prime number. If we add 3 and 4, I guess that'll give us 7. That should be a prime number. And then on our moq store object here, we can assert things. So we can say moq store object verify, and we want to verify that some method on our that's defined by our interface is being called, and let's imagine that's going to be called save. So if we pass in a lambda expression on some moq such that the moq.save method was called, and we want to make sure it was called exactly one time. And so we can say times, somewhere down here, times once. And that's our test written. Now you can see there's a lot highlighted there in red, so there's a lot of code creation and refactoring to be done. That's fine. Let's start by creating our iStore interface, and that might look something like this. Very, very simple interface. It just defines one method called save, which takes a result parameter. So that now satisfies our iStore. You can see here string calculator is complaining because it does not have any such constructor that takes an instance of iStore. So let's go and fix that now. So down to our string calculator. For now, I'm going to leave the default constructor alone, which is that. And I'm going to add a new constructor which takes an iStore store, and I'll persist this to a backing variable there. And then if we look at our logic that's going to be required, we're going to need some method to check if a number is prime. So that method might look something like this. Is prime. Now my method for checking if a number is prime is open to debate, perhaps for another demo, but there's a method, some method to check if a number is prime. And so we're now going to need to just refactor the logic here before we return this total to say, okay, if our store is not null, we can check if is prime our total, then call stores.save method on the result. And then when all of that is done, just go ahead and return the result as normal. So hopefully that is some kind of implementation of the logic that's going to be required. If we come back to our test, we can see here that our save method is now satisfied, but the save method expects some parameter, some kind of integer. We don't know what that integer might be, so we can use another feature of mocking. It is any, and it's any of type int, and that will go ahead and satisfy that condition for us on our moq object. So we now have a test that's buildable. Let's see if we can run it. Visual Studio is having a think about it. And we can see here that all our tests are passing, so that's great. So quickly, let's have a run through the test to try and make sense of it once more. So we've created a new iStore interface that we're going to be passing into our string calculator. And the iStore defines a save method. We've got new logic inside our string calculator to say that when we call this addition method, if the outcome of our addition is a prime number, we want to assert that save gets called. We don't care yet how it works or what it does. We just want to assert that it gets called. And we can use our mock object verification tools here to verify that save with any integer gets called just once. And that test is passing. For the sake of the demo, I'm going to refactor my string calculator class to get rid of this default constructor. And so now string calculator can only be instantiated with an iStore. And so that now is obviously going to break my factory method here for getting a calculator. And hopefully this will prove the point of this factory method. If I did not have this factory method in place, I would have broken every single test that I had previously written. But now I just have to refactor one single factory method. And it might be refactored to look something like this, where I take my mock of iStore and turn it into a class-wide private field. And then my get calculator news that up and passes it into a new string calculator and returns that. And down to my test method, I'm going to refactor that to adhere to this new refactoring. And we're going to say we don't need the mock store anymore. And the calculator is now calc get calculator. And then the mock store we're using is the class-wide variable mock store. And if we run that, we see Visual Studio has a build and has a little think about it. And hopefully we'll see everything building successfully, and we do. Great. Once I have this test refactored, I can then turn it into a parameterized test. Thus, so here I'm going to write, I think, 5 tests here. So I'm testing 2. 2 is always a good edge case for primes. I'm testing 5 and 6, which should give me 11. 3 and 4 should give me 7. 10, 10 and 3, 23, and all the 5s, and this 3 should give me 53. All of these should be primes, and so hopefully save will get called for all of these tests. So let's run this. And we should see 5 new tests, and hopefully they'll all pass. And indeed they do. And just as we're testing that save gets called when a number is a prime, we should then test that save does not get called if the result is not a prime. So a new test for that. So our test cases now are results that should not be prime. So 4 on its own just gives us 4. If we add in 5 and 5, we get 10. 5 and 4 gives us 9. 25 and 51. So none of these numbers are primes. And my new test here, the signature reads that for the add method, where the result is not a prime, inputs and results are not saved. And so again, I'm just calling a string calculator, calling add, and I'm verifying this time that the save method gets called never. And I just need to pass in a some integer to satisfy the save method, and we can now run this test, and hopefully this too will add 5 new tests that all pass. Looking good. We can see, great, we have everything passing. So we're testing now that we have fully tested our save logic, that it does seem to get called whenever the result is a prime, and that it doesn't get called when the result is not a prime. Moving on to integration testing, let's imagine that the customer has now specified how they want their results to be saved in the case where they happen to be prime numbers. And they've told us that they want to save the results simply to text files on disk. And so this brings us to integration tests. And integration tests are really tests that rely on some infrastructure. They might rely on maybe a web service or database, or in this case, the file system on the computer that's running the tests. So I've done some refactoring here just to show you what's going on. I've taken the iStore and the string calculator that we were working on in our test class before, and I've just moved them into their own new assembly called testdemo.calculator. I haven't changed them in any way, I've just literally moved them around. I've created a new assembly for integration tests. I've just created one new test harness here called string calculator integration tests, and as you can see I've done no work in there whatsoever. And our old unit test class is exactly as it was. It's just that this unit test class now has a reference to our calculator class. And if I run my tests, you'll see hopefully that everything is still building and we get 28 passing tests. So let's start talking about integration testing. Let's create our first integration test. And so here, before I talk about the test, let me just satisfy some of these references. Here with the test itself, we're testing the add method of the string calculator. Where the result is a prime number, we're checking to see do we get a file created. We're not yet concerned about what's in the file, we just want to check that the file exists. So I'm creating a path to some file here. I'm going to use some implementation of the iStore interface that I'm calling file store, and that has yet to be written. I'm passing that into my string calculator, I'm calling the add method, and then I'm just checking to see does a file exist at this file path. So let's create our file store class down here. File store class might look something like this. So it implements iStore. As part of its constructor, it takes a path. As part of its save method, it takes a result and it just saves that result to a text file at the file path. If we now run this test, and if this test passes, it means that we do actually have a file at the expected location. And if I open Windows Explorer, in the temp folder, we can see, yes, we have this test.txt file. And if I open that file, you can see in here we have value 7. Now we're not testing the value yet, we're just testing the existence of the file. But just for eyeballing, you can say that 3 and 4 would have equaled 7. I wonder if you notice any issues with this integration test. Let's say this file here already exists. Well, if that's the case, this assertion is always going to be true. And you know, it's more than possible that this file might exist. Somebody might have run this test yesterday, and I come along and run it today, and yesterday's test created the file, so therefore it already exists, and the test is going to pass no matter what. So therefore this test as it stands is unreliable. So what we need is a way of setting up and then cleaning up our infrastructure before and after we test, and test harnesses provide us with a means for doing that. We can use methods, maybe we might call them setup and cleanup, something like this. And what we do with these methods is we decorate them with specific attributes, and in this case for NUnit we use test fixture setup. And what this attribute does is it means that once we have it in place over a method, this method is going to be called before each and every test runs. Inside our setup method, we might want to check if the file that we're testing exists, and if it does exist, we'll then delete it. And so therefore I'm going to need to take this file path variable and make it class-wide. So let's do that. Let's move it up here and turn it into a private class-wide field. And we'll just call it underscore file path. And so our setup method now checks if that file exists, and if it does, it just deletes it. Down to our test, let's refactor that to use the class-wide variable. And now let's run our test. So what's happening now is that when the test entry point is reached, we come up and we run our test fixture setup class. We check if the file exists, if it does, delete it, and then we come back and then run our test. And we can see here everything is working, so that's great. And wouldn't it be nice then if when we're finished testing and we've run all our tests that we can leave our infrastructure clean and leave it the way we found it in the first place. And we can do that, and we might create a method, maybe we could call it cleanup, something like this. And with cleanup we can use another attribute, test fixture teardown. And when a method is decorated with this attribute, it will be called each and every time a test has completed. So for each test that I write in this class, every time that test has finished running, this cleanup method will be called. And again, I'm going to use the same logic in the cleanup method, and it'll be, okay, if the file that I'm looking at exists, just get rid of it. Just clean up my my environment and let me get out of here. So let's run this test again. So what it'll do is it'll check if the file exists. If it does, delete it, then run the test, create the file, and then when the test has finished and the test assertion has completed, we'll go away and we'll clean up our environment. And we can see here everything is passing, and if I actually go to my temp folder, we'll see that we're leaving it empty. There's no files left in there, they've all been deleted. So that is how we can use test fixture setups and teardowns. So let's create one more integration test, and this time I'm going to check the contents of the file. We create a test that looks something like this, where we're testing the add method, where the number is prime and it writes correct result to file. So this time I'm creating a new file store, and I'm passing that store into my string calculator, and I'm adding 3 and 4. And let me just fix that reference there. And there, when I add 3 and 4, my expected result is going to be 7, which I know is a prime number. And so therefore then I'm going to say, right, stored result, go to the file system and actually read this file stored at this variable and get me the first line. And then I'm going to assert that that stored result is equal to my expected result. So let me run this test. And we now have 30 tests passing, and we can see that this test has passed. So what's gone on here is that we've created the file, the test has actually opened the file, read the first line, and it's asserting that it indeed is returning a string value of 7.